Hi everyone. This time we are going to talk about the pressure at depth equation. How do you calculate the pressure on something when it is deep inside of a fluid? And we're going to derive this equation. I don't do an awful lot of equation derivation in this course, but this one is simple enough and I want you to see where it comes from. So let's say I have a column of fluid and I'm going from the bottom to the top of the fluid. And that column has some sort of an area and it has some sort of a height. Okay, you and I both know that pressure is force divided by area. And we're talking about the weight of this column of fluid. So this is going to be the force of gravity, which is mass times acceleration of gravity. So I'm going to take mass times acceleration of gravity and I'm going to put it in for force. So pressure is going to be mass times acceleration of gravity divided by area. All right. Now, we know that density, rho, is mass per unit volume. So I'm going to rearrange this and I'm going to solve for mass. So the mass of this column of air is going to be the density of the air times the volume. So I'm going to replace mass over here with density times volume. So I'm going to shove that in to that, and I'm going to get pressure is density times volume times acceleration of gravity divided by area. We're really close. Okay. Now, for a column like this, the volume of the column is going to be the area times the entire height. So the volume of the column is going to be the area times the entire height. So I am going to replace area and height with the volume. So the pressure is going to be the density times the area times the height times acceleration of gravity divided by area. Well, I've got area on the top, area on the bottom. Same thing, top and bottom. What happens? They're going to cancel. And what I end up with is this equation. Pressure is density, rho, height times acceleration of gravity. And that actually is my pressure at depth equation. So here it is one more time. The pressure at the depth in a solution or a fluid is the density of the fluid, the height of the column of fluid, and our old friend acceleration of gravity. So put this equation on your formula sheet, make sure you understand what units it's going to be in, and we're going to use it after a bit. But let's talk a few things about what this all means. When you're doing problems, you're going to have some problems that are going to refer to gauge pressure. Now, gauge pressure is what is actually read on a pressure gauge. That's kind of common sense. But if you are asked to find the total pressure on something, it's going to be a combination of gauge pressure plus atmospheric pressure. Let me give you an example. Let's say I've got a diver, and due to the weight of water on top of this diver, maybe this diver has 3 atmospheres of pressure pushing down on this person. But this person is on planet Earth, and above the water, there is 1 atmosphere of air pressure also pushing down on them. So what is the total pressure that's actually on this diver? 1 atmosphere for air, 3 atmospheres for the fluid, and the total pressure on the diver then would be 4 atmospheres. So just read the problems carefully if they ask or say something about gauge pressure. Now, our pressure at depth equation is density, height times acceleration of gravity. So what does that mean? First off, what the equation says is the shape of the container doesn't matter. It doesn't matter if you've got the only thing that matters is height. So it doesn't matter when you're going from the liquid up to the child's mouth if you have a straight straw or if you have a silly straw. Doesn't matter. The shape of the container does not matter. If you want to measure the pressure down at the bottom of this little gizmo here, and this is a classic demonstrator that is in most physics classes, the pressure at the bottom is going to be the same everywhere, even though the shapes are very different. And it's because the shape of the container doesn't matter. Why is that a good thing? It makes our math so much easier because we don't care about the shape of the container. All we care is the height, top to bottom. Another thing that the equation says is if there is a difference between heights, there's going to be a change in pressure from the top to the bottom. Well, ladies and gents, I don't know if you live where you have water towers, but a lot of the flat, open country in the Midwestern part of the United States has a lot of water towers because it's flat. And the only way to get water pressure is that they have some sort of a pumping station, pumps the water up into the water tower, and then it's the pressure of the water falling this great distance that actually gives pressure into the pipes into people's homes. Now, not everyone is going to have the same pressure inside their home. That is going to be determined by the difference in height between where the water is pumped from and where your house is. So the water tower is always going to be the highest point, higher than any one of the consumers getting the water. So the people who live lower than the water tower are going to have relatively high pressure. Somebody who lives on a higher hill, even if they're further down and further away from the water tower, are going to actually have lower pressure. And someone who is very, very low, big change in height from the water tower, they are going to have the highest amount of pressure. So they can all be on the same water main, but it's those differences in altitude that are going to determine the pressure of the water coming out of their pipes. Here's the other cool thing this equation says. The diameter of the pipe doesn't matter, just the height of the column. So if you have a skinny pipe, medium pipe, fat pipe, it doesn't matter. Height's the thing that's going to determine pressure, not the diameter of the pipe. So if you've got a water tower that goes from here down to the water main down here, it doesn't matter that this is a fat part of the water tower and this is a skinny part of the water tower. It's the height that's going to determine pressure, not the fact that part of it's a fat pipe and part of it's a skinny pipe. It is just going to be the height that determines the pressure. All right, that will do for this time. We're going to come back and do a pressure problem in a little bit. See you then.